As a continuation, we will be having a brief discussion of dual values in this section. The concept of a dual value was introduced in the previous chapters. Let us recall that the dual value is the change in the value of the optimal solution per unit increase in the right-hand side of the constraint. The interpretation of the dual value for nonlinear models is exactly the same as it is for linear programs. However, for nonlinear problems, the allowable increase and the decrease are not usually reported. This is because for typical nonlinear problems, the allowable increase and decrease are zero. That is, if you change the right-hand side by even a small amount, the dual value changes as well. There are several linear programs that were built to model different client attitudes toward risk. So in this section, we are going to study a very important related application, which is constructing an index fund. So what is an index fund? Index funds are an extremely popular investment vehicle in the mutual fund industry. Indeed, the Vanguard 500 Index Fund is the single largest mutual fund in the United States with more than $176 billion in net assets in 2014. An index fund is an example of passive asset management. The key idea behind an index fund is to construct a portfolio of stocks, mutual funds, or other securities that matches as closely as possible the performance of a broad market index such as the S&P 500. So, why are index funds so popular? Behind the popularity of index funds is a substantial amount of research in finance that basically says you can't beat the market. In fact, the vast majority of mutual fund managers actually underperform leading market indexes such as the S&P 500. Therefore, many investors are satisfied with investments that provide a return that more closely matches the market return. So we have here an example of constructing an index fund from the Lehman Brothers Investments. Lehman Brothers has a substantial number of clients who wish to own a mutual fund portfolio that closely matches the performance of the S&P 500 stock index. A manager at Lehman Brothers has selected 5 mutual funds that will be shown in the table in the next slide, and that will be considered for inclusion in the portfolio. The manager must decide what percentage of the portfolio should be invested in each mutual fund. So the selected mutual funds were the International Stock, Large Cap Blend, Mid Cap Blend, Small Cap Blend, and the Intermediate Bond with the corresponding annual returns and the S&P 500 return in each scenarios. The decision variables used in the model presented in the slide represented the proportion of the portfolio invested in each mutual fund. IS represents the proportion of portfolio invested in international stock, LC for the investment in large cap blend, MC in mid cap blend, SC for small cap blend, and IB for the proportion of portfolio invested in intermediate bond. And for clarity of model exposition, we introduce variables R1, R2, R3, and R4, which measure the portfolio return for each scenario. Next is to define the objective function. The objective is for the portfolio returns to match as closely as possible the S&P 500 returns. So to do so, we might try minimizing the sum of the deviations given in the equation. Since we want to get as close to the target returns as possible, it makes sense to assign a higher marginal penalty cost for large deviations than for small deviations. So a function that achieves this goal is when we square each term. It is where positive and negative deviations do not cancel each other out, and the marginal penalty cost for deviations increases as a deviation gets larger. So the complete mathematical model that was developed involves 9 variables and 6 constraints, including the non-negativity constraints. This minimization problem is nonlinear because of the quadratic terms that appear in the objective function. For example, in the term portfolio of return in scenario 1 minus 13 squared, the variable of R1 is raised to a power of 2 and is therefore nonlinear. However, because the coefficient of each squared term is positive and there are no cross-product terms, the objective function is a convex function. Therefore, we are guaranteed that any local minimum is also a global minimum. This table shows a comparison of the Lehman Brothers portfolio return versus the S&P 500 return for each scenario. So as you have noticed how closely the portfolio returns match the S&P 500 returns. So we just illustrated a very important application of nonlinear programming in finance. In the next section, we show how the Markowitz model can be used to construct a portfolio that minimizes risk subject to a constraint requiring a minimum level of return. Before we talk about the Markowitz portfolio model, let us first have a little background about Harry Markowitz. So he received the 1990 Nobel Prize for his path-breaking work in portfolio optimization. The Markowitz mean variance portfolio model is a classic application of nonlinear programming. So in this section, we present the Markowitz mean variance portfolio model, where the numerous variations of this basic model are used by money management firms throughout the world. A key trade-off in most portfolio optimization models must be made between risk and return. In order to get greater returns, the investor must also face greater risk. So the index fund model of the previous section managed the trade-off passively. An investor in the index fund we constructed must be satisfied with the risk or return characteristics of the S&P 500. Other portfolio models explicitly quantify the trade-off between risk and return, while in most portfolio optimization models, the return used is the expected return or the so-called average of the possible outcomes. As an example for this portfolio model, let us consider the Lehman Brothers example developed in the previous section. So there were 4 scenarios, and the return under each scenario was defined by the variables R1, R2, R3, and R4. If P sub S is the probability of scenario S and there are n scenarios, then the expected return for the portfolio mean of R is equal to the summation of n, where S is equal to 1 times P sub S times R sub S. If we are going to assume that the 4 scenarios in the Lehman Brothers model are equally likely, then it will be mean of R is equal to the summation of 4 scenarios, where S is equal to 1 times 1/4 times R sub S, or mean of R is equal to 1/4 times the summation of 4 scenarios, where S is equal to 1 times R sub S. The measure of risk most often associated with the Markowitz model is the variance of the portfolio. For our example, the portfolio variance is equal to summation of n to S is equal to 1 times P sub S multiplied by R sub S minus mean of R to the power of 2. And for our example, the 4 planning scenarios are equally likely, thus giving us the formula of variance is equal to summation of 4 scenarios to S is equal to 1 times 1/4 multiplied by R sub S minus mean of R to the power of 2, or variance is equal to 1/4 times summation of 4 scenarios to S is equal to 1 multiplied by R sub S minus mean of R to the power of 2. The portfolio variance is the average of the sum of the squares of the deviations from the mean value under each scenario. The larger this number, the more widely dispersed the scenario returns are about their average value. So if the portfolio variance were equal to 0, then every scenario return R sub I would be equal. So there are 2 basic ways to formulate the Markowitz model. First is to minimize the variance of the portfolio subject to a constraint on the expected return of the portfolio. And the second one is to maximize the expected return of the portfolio subject to a constraint or variance. So consider the first case. Let us assume that Lehman Brothers clients would like to construct a portfolio from the 4 mutual funds, 5 rather, in the previous tables, and that will minimize the risk as measured by the portfolio variance. So however, the clients also require the expected portfolio return to be at least 9%. In our notation, the objective function is minimize 1/4 times the summation of 4 scenarios to S is equal to 1 multiplied by R sub S minus the mean of R to the power of 2. The objective for the Markowitz model is to minimize portfolio variance. Note that the equations from the scenario 1 through the scenario 4 were present in the index fund model presented. So these equations define the return for each scenario. The equation IS plus LC plus MC plus SC plus IB is equal to 1 is required that all the money must be invested in the portfolio. So this constraint is often called the unity constraint. The equation 1/4 times summation of 4 scenarios to S is equal to 1 times R sub S is equal to the mean of R is to define the expected return for the portfolio. The equation mean of R is greater than or equal to 9 is the portfolio return must be at least 9%. And lastly, the non-negativity where IS, LC, MC, SC, and IB is greater than or equal to 0. As a conclusion, the Markowitz portfolio model provides a very convenient way for an investor to trade off risk versus return. In practice, this model is typically solved iteratively for different values of return. So in finance, there is a graph called the efficient frontier. So each point of this graph is the minimum possible risk, which was measured by portfolio variance for the given return. And when you're going to look at the graph of the efficient frontier, an investor can readily pick the mean variance trade-off that he or she is most comfortable with.